Hello, and welcome to another IoT Central workshop. Please send any questions you might have in the chat, and we will follow up with any unanswered questions using the email address you registered with. My name is Shawn Hymel. I'm a developer relations engineer with Edge Impulse, and today we're going to talk about data curation, what you can do prior to ingesting your data into Edge Impulse, and feature scaling, why that's important, why you should be doing it, and an example of how you might go about doing feature scaling. Edge Impulse is the world's leading embedded machine learning platform. It helps you build a full end-to-end machine learning pipeline to accomplish a variety of machine learning tasks, from regression to vibration and sound classification to object detection and predictive maintenance. You can import data from any sensor and deploy your model to nearly any device. You maintain control of the data and firmware the whole time. The Edge Impulse Studio is an online platform that handles everything, including collecting data from your embedded sensors, labeling that data, performing any pre-processing calculations, and training machine learning models. This end-to-end project is what we call an impulse. You can then test your impulse on live data with a connected sensor. After, the studio will guide you through the process of creating firmware or a library that will run your impulse on any number of platforms. This includes your pre-processing code, trained neural network, and any anomaly detection code you may have so that you can perform inference locally without an internet connection. Let's look at an example of sensor fusion, why we might want to do something like feature scaling. Let's say that we have one sensor that's gas data, and that gives us an output of something like 0 to 10,000 parts per million, and we also want to pair that up for whatever reason with an accelerometer, and that gives us something like -10 to +10 g-force. As you can see, there's a little bit of a difference between the scales from these data sources. One goes from 0 to 10,000, the other goes from -10 to 10. Let's say our loss function, the one used to help train our neural network, is a function of our weight vectors, and W1 is a collection of weights for the X1 input, W2 is the collection of weights for the X2 input. Let's graph that loss function. For example, here, we might get something like this. It's a very simple inverse hill. A real loss function for most complex or deep neural networks are going to be a lot more complicated than this. We can view this as a contour map, with the middle being the lowest point. Imagine looking at a 3D map straight down and we're plotting the contours like you would see in a geographic map, a contour map. Notice that there's a difference between the scales in the data. The weights of the neural network will be scaled appropriately. For example, the W1 weights have a smaller range than the W2 weights to offset the larger scale of the X1 inputs. During training, updates are likely going to bounce around, which means longer training times. And with more complex loss functions, you're more likely going to end up in a local minimum rather than the global minimum, which isn't ideal in most cases. So what happens if we normalize this data? And by that, I mean we take the scale of both of our sensor channels and squish them so that they are essentially in the same range, let's say between 0 and 1. The weights now have similar ranges, and the training updates are going to move to the optimum faster because there's no need to bounce around in that oblong shape. We're also less likely going to end up in a local minimum. So, as you can see, having similarly scaled inputs to our neural network helps speed up training and potentially makes the model more accurate. So how do we do this feature scaling? If the input looks something like a Gaussian distribution, the common way to do scaling is to do something called standardization. This is where we subtract out the mean of the data and then divide by the standard deviation. In effect, this produces a new set of data that has a mean of 0 and a standard deviation of 1. If your data does not have a Gaussian distribution, we can do something called normalization, and you will often see ranges something like 0 to 1 or -1 to 1, but in this case, let's assume normalization means adjusting the range of your data to be between 0 and 1. All we do here is we take our input, subtract by the minimum possible value, which we get by looking at the entire or the training data set, finding the minimum value, and that's our minimum here. We then divide that by the range, which is the maximum value in our training data set minus the minimum value. Now that you've performed feature scaling, you've trained your neural network or your machine learning model, what happens when you go to deploy it to your device? Your trained model will expect the same inputs. In this case, those should be the scaled inputs. And this holds true for whenever we're collecting new data for inference, and that means we have to scale that data too. We usually can't collect a lot of data to compute new values for the mean, standard deviation, or minimum or maximum when we're collecting in the field during inference after our deployment. So we need to remember the values for scaling that we computed using the training data, which is your standard deviation, your mean, your minimum or your maximum, depending on if you're doing standardization or normalization. We have to remember those values that we computed during our pre-processing step and then use those values in order to do feature scaling during inference prior to feeding the raw data to our model. Let's take a look at an example of this. If you head to github.com/edgeimpulse/course-embedded-ml-capstone, you will find some of this project information that we're working on here. Go to 01 Dataset Curation and Feature Scaling. In it, you'll find a Google Colab notebook. Let's click the Open in Colab button. Make sure you have a Google account in order to run this. Feel free to read this information. It's about why we want to do normalization and standardization, just like we talked about, but there's a link to an actual academic paper to support it. So press Shift-Enter to run it. And the first thing we're going to do is read this data from the CSV files. We're going to be using the data set that we collected in the workshop where I showed you how to collect the data using the accelerometer and the gyroscope. So we're going to open up our file browser over here, right-click, say New Folder. Let's call it Dataset. Note that it needs to match this dataset path down here, so everything's in content. And we're going to want to create a dataset folder. Right-click on Dataset, click Upload. If you download that GitHub repository, you'll see it here. If you go into Datasets and Magic Wand, this is that dataset that we collected, or at least the one I did during recording of that video. So Control A to select all of them, or Command A if you're on Mac. Click Open and give it just a moment while it uploads all of that data. Make sure that all of the settings look correct. So we work in the home path, which is content, and then the dataset directory is in there. We're going to be splitting apart this dataset into training and testing sets, where 20% is saved for testing, and that will be uploaded to Edge Impulse. The rest is for training and ideally validation. So once the uploading is done, you can close that folder, and we're going to want to run these cells. So Shift-Enter to run the cells. Click Run Anyway, and I forgot to import my stuff. So let's go back here to this cell. Shift-Enter to import all of the important packages. Shift-Enter to set all of these settings or parameters. The next thing we're going to do here is simply read in the values from the CSV files. So feel free to look at one of these. This should look just like the CSV files we captured in that previous microsession. And you can see it's actually broken apart quite nicely into these tables for us because that's what Colab does. But there's the timestamp over here, which we're going to keep, and we're going to feed that into Edge Impulse because that timestamp column is required. We then have accelerometer XYZ and gyroscope XYZ. Notice that the accelerometer scale is a little bit different than the gyroscope scale. Now, we could probably train a model and it would work fine with these raw values, but for the sake of demonstrating how you might go about doing standardization, let's walk through that in this notebook. So close out of this CSV file. We can close the file browser, and this cell simply goes through each file in that directory, and it's just going to read the header, check the shape to make sure that the data all looks the same, and it's going to append these samples to a collection of samples that we will be able to use and analyze. So let's run this cell. In just a second, you will see the header information that was read from each of the CSV files. The data set shape, we have 400 samples. Each sample contains 100 readings, and there are 7 columns, which should correspond to the 7 different header names here. We also see that there are 400 samples and 400 files. It remembers these file names for you so that it's going to recreate them with the new standardized data. Next, we're going to split the data set, and feel free to work through this code more slowly. I don't have time in this workshop to go through every single line, but this file is available for you to work through and analyze to see what's going on. What we're going to do is shuffle all of the samples, and then we're going to extract the first 20% in order to be our test set. Because it's been randomly shuffled, that counts as good enough randomization to pull out a random set of 20%. The rest, the 80%, will go into our training set. And remember, Edge Impulse doesn't have a validation set. It automatically extracts that from your training set when we upload it. So let's run this cell, and you will see that 80 of the samples, 80 random samples, are now in our test set, and 320 samples are in our training set. Next, we want to analyze this data. So we have a helper function here that will flatten the data for us. So it's going to take all of the samples and create one sample that's just a long string of individual value numbers, because we want to analyze all of the data in aggregate, not as individual samples. Then we're going to print the histograms, and notice we're only using the training data here. We're setting aside the test data set because we don't want that to influence how we set up our pre-processing. Notice here that our data looks fairly Gaussian. The accelerometer XYZ and the gyroscope XYZ, these actually look pretty Gaussian. So we are welcome to use standardization here as opposed to normalization, which is what we're going to do. But notice the scales. About -10 to 10, about -20 to 20. Okay, so this is, on the order of about 40, a range of about 40. As opposed to here, on the gyroscope, we're looking at a range of about 400. So order of magnitude difference between our scales. Like I mentioned, probably not a big deal if we feed this data directly to a neural network for training, but just to make things easier for the training process and for inference down the road, hopefully get a more accurate model, we're going to go ahead and standardize this data. But so you can really see what this looks like, first, let's print them, or let's plot them using the same scale. So about -500 to 500, you can see the accelerometer data is on a much different scale than the gyroscope data, hence why we want to standardize the data. I have a function here that will calculate the mean, standard deviation, minimum, and range for each of our channels. And that's important because if you look above, we don't want the mean and standard deviation and minimum and range for all of this data. We want it for each channel. The accelerometer, X, Y, and Z are 3 individual channels, as well as the gyroscope, 3 channels you see here. We want to perform standardization along each channel. So we're going to use this function. We're going to need another function to perform standardization. And this is that equation I showed you earlier, where we get the input values, we subtract the mean, and then we divide it by the standard deviation. That's it. It just matches that formula I showed you. Then we're going to actually compute the metrics. This gives us the means, standard deviations, minimums, and ranges for each of the channels. So 1, 2, 3, 4, 5, 6. Notice that we have dropped the timestamp column because Edge Impulse does not look at this. It just uses that to work with time series data. And so you need to remember the means and standard deviations going into inference. You will need to actually copy these values and paste them into your C or C++ code, if that's what you're writing with, on your actual device in order to perform standardization of any new incoming values we get to perform inference on. So next, we standardize each channel. This just walks through and looks at each channel in our training set and standardizes that data. It also does it with the test set. However, notice that we are using the means and standard deviations that we calculated from the training set, and we're using those to standardize the data in the test set. And that's because if we had used the values in the test set to calculate the means and standard deviations, that would introduce some sort of bias. Now, how much of a bias? Probably not a lot, but in the sake of let's keep the test set truly as a test, that's why we are using the means and the standard deviations that we calculated just from the training set. So we've run that cell, and you can see we've got the shapes again, which is good. Now let's examine the histograms once more. You don't want to copy these means and standard deviations because everything has been standardized. So Our means and standard deviations should all be 0 and 1 respectively, as you can see here. That means it worked. Sure enough, take a look across our histograms, and you can see everything is a mean of 0 and about a standard deviation of 1. Great, everything is on the same scale now, which is going to make training so much nicer. Now, it does mean that we have to do a little bit extra math during the inference stage, but hopefully this creates a better, more robust, more accurate model for us. Finally, now that we have all of that data normalized or standardized in our case, we are going to save those all back to a CSV set of files, just like we had before. In fact, don't mix these up because I believe they are named the same thing. If you work through these cells, it's going to print them all to CSV files, and it's going to zip them up into a out.zip. We will download that file. Let's go to downloads. Great. Save it. Open this. Let's unzip this file, extract all. And if you go into here, you can see our training set that's been nicely divided. And we've got our test set that's also divided, meaning we've got about 20% in here and the rest 80% in here. Let's open a new web page to edgeimpulse.com. Make sure you are logged into your account. I'm going to create a new project. I'm going to give it a name like My Magic Wand Standardize so you can see how this is working. Let's X out of that. We will go to data acquisition. And from here, we will upload existing data. As before, we can use CSV files. So let's choose a files. We will want to go to downloads, go to out. We will start with training. So Control A or Command A to select all your training data. Select open. We will select training because that is our training set. And we're going to let it infer from file name because as you saw, those files each started with a label, and that's what we want to use for our file name. This is following exactly what we did in that other episode where we named our CSV files with the labels. So let's start the upload and wait just a moment while that finishes. Once it's done, choose files again. Let's go to test, select all of those, select testing, once again infer from file name, and upload all of those. Great. Let's go to data acquisition. And here you should see alpha, beta, gamma, unknown. These are the samples that we collected. Feel free to click on one. And sure enough, our data is nicely scaled. So we don't have things between several hundred or dozens of values. Everything's kind of nicely between about -3 and 3. And if you click through these samples, you can see that. Let's look at a beta example. Click on one of those, and sure enough, everything is nicely in that scale. All of these channels fit nicely within here. Now that we have our data set imported to Edge Impulse, we are ready to train our model, which we will save for another time. I want to thank IoT Central for hosting this workshop. You can find more workshops and Edge Impulse microsessions at iotcentral.io, where this video will also be available on demand starting tomorrow. If you have any questions about Edge Impulse, or you'd like to show us something you've built with Edge Machine Learning, please create a post at forum.edgeimpulse.com.